Hey everybody, we are back for five, week five. All right. Um, I will be finishing up stats this week, at least in lectures, which is good because you're kind of moving into that part of the exercises real soon now. Maybe a little bit ahead. I feel like my timing is set up for like having a few holidays here and there, which we don't have this semester. Maybe that means we take a week off. Maybe that means we just end a little bit early. We'll see. We'll find out. Okay. We were in here. And I had done some stats and we had looked at p-values and said, okay, look, there's you get a p-value and you look at that p-value and say, well, if it's less than 0.05, the thing we've chosen as our alpha, this one is very much less than 0.05, then we will reject the null hypothesis and say, okay, that is false, and I conclude that the alternate is true. That's just the game of inferential stats that we're playing. So we say, okay, the null hypothesis, and this is an ANOVA, the null here, because I looked it up on Wikipedia or whatever, is that all four of those groups have the same mean. So I conclude, no, they don't. Okay. Well, this is still fundamentally a probability. Well, what's going on here, I think is something we have to have in mind, you have to have in mind, and even just as someone looking at other people's stats and sort of evaluating other people's analysis, this is something we need to know about. So basically what's going on is every time we do a statistical test, we have this 5% chance of coming to a false positive, like incorrectly coming to a conclusion that there's something going on here. One of the ways you can sort of play with that and again come to a non-valid conclusion that looks valid is by effectively designing your experiment this way. And this is totally tempting, right? You go out and for some process where data points are not cheap, right? So this could be, I have to go out and do a survey, or I have to like, do a whole bunch of like observations in the wild, or maybe in a computing context, it might be like, I just have to run the code overnight for each data point or whatever. It's really tempting to sort of every day as you do that, have a look and just see, oh, is p less than 0.05 today? Nope. Well, I'd better go out and collect another data point then. It's very easy to write that as if that's not what you did, right? You can write the summary of this experiment and just say, I collected 13 data points. Why did you collect 13 data points? Somebody might ask. Well, it's because when I collected 12 data points, p was 0.051, and with that one more data point, it became 0.459. This is, I think, clearly dishonest. I think you should know not to do that. It's easy to do it without sort of being that explicit about it. Maybe I'll say that. Or, again, remember that every time you do a statistical test, by sheer chance, you can come to a conclusion. So that, again, this is a scenario where the means are absolutely the same, or whatever the null hypothesis is in our story, is absolutely the truth. Still, 5% of the time, you will get a small p-value because that's what it is. So if you do a bunch of statistical tests, and you can imagine this, right? Especially when you have like a rich data set. I feel like the data set in the stats book is so often just like, oh, here's 2 columns and you need 2 columns and then you can do the t-test. A lot of data sets aren't like that. They just have a whole bunch of data in there and you can play around and you can do a lot of different stuff with it. And what do I do? I guess in my story here, I've got some kind of like study of various fitness markers in Canadian cities. And I can say, well, I think that different cities have different, no. I think that different cities have different, no. I think that, okay, the thing is, there's too many cities here. I just want to look at the, no. Okay, the problem is it's not the major cities versus the small, okay, right. You can, it's so easy to talk yourself into that just, I'm just going to do a whole bunch of different tests until I find one. But that thing that's going on means that every time you do another test, and of course it's very easy, once again, when you're writing it up, it's very easy to say, well, I didn't really do those didn't really get me any results. The only thing I really did was that, and that's the only thing that appears in your sort of report or whatever. And then just say, oh, p less than 0.05, hooray, I'm smart. Of course, there's a relevant XKCD, there always is. And the very XKCD punchline here is like, if you look at these 20 panels, one of them has a small p-value, and if you only look at that panel, ignore all the other ones, you get a conclusion. That's the story of just things are happening by random chance. So as soon as you do multiple tests, we have this problem. And if you do multiple tests, I talked last week about the Bonferroni correction. That's a thing you can do. But at the sort of more meta level, it's very easy to look and say, okay, well, I started this, I gathered all the data, and I looked at the t-test. Oh, but then I looked, and I realized they're really not normally distributed. I should not do a normal, I should not assume a normal distribution here. So, okay, I can't have done that. That's reasonable. Or I guess that's my version 2 here. This was like, I'm doing something like this, and I look at weight by city, and I'm hype, but then I realize, like, I don't know, maybe people in Calgary are taller than people in Vancouver or whatever, right? So looking at weight in the absence of height doesn't make sense. You have to do body mass index or whatever. So that's just, I did an analysis that I just realized was a stupid thing to do now that I kind of think a little more carefully about it. Or I did that first analysis and the p-value was big, but if I do this other analysis, the p-value is small. All of these look the same. Like if I showed you a Jupyter notebook, the code is exactly the same in all of those cases. You sort of have to know what was in my heart to decide, like, because again, I think these first two are totally valid. This last one is fishing around, doing analysis until you get significant results, which is a fancy way to say lying, but with stats. In exercise 5, that is in the future still, I'm asking you to do a whole bunch of inferential stats tests. And of course, you're going to do it because I asked you to do it. It was the exercise that you're being presented with. Are you coming to a valid conclusion in this way or not? You have to know what was in my heart when I wrote that exercise, I guess. It means a little bit you have to plan ahead. If you're doing like serious, like biomedical stuff, like looking at, is this, doing a drug study or something like that, the sort of gold standard of the way to do that is to, step 1, publish your plan. Say, I am going to do this. I am going to measure this many people. I am going to measure this thing that's going on in their blood. I am going to do this analysis on it. That's how I'm going to come to a conclusion. And then they give you the money, and then you do the study, and then you sort of, you've been very public about what your plan is, because that's the sort of most honest way to do it. Otherwise, it's very easy to end up in this case, and it's impossible to tell if you just don't publish all of that, right? Like, if I did all of this somewhere in a Jupyter notebook, but then when I publish the paper, all I publish is this and all I mention is that, well, I'm lying. In this, formerly before, somebody bought 538, was it? New York Times or the Post. Anyway, somebody bought this wonderful website and destroyed it. Somebody else, some other delightful human has recreated it. So what's happening here is we have this data on a bunch of stuff, right? Whatever is going on, how all the various ways you measure goodness of the economy, I guess. And you choose which team you're on, and how do you decide which group is in power at any moment? So, are we currently in a Democrat world or a Republican world? You can kind of pick and choose which one's which. And you can then look at, well, what do I mean by good economy? And, oh, okay, I've just realized that if I think that these two things are the indications of Democrats being in power, and I look at GDP and stock prices, Democrats are good for the economy, and I could, I have a very small p-value, and I can publish that result. But if I play around a little bit, I realize, oh, I've actually just suddenly realized that Democrats are bad for the economy. And I publish the article in the newspaper, and I cheer if my team is better than your team or whatever. All of these are just effectively different statistical tests. And, there's probably more than just random chance going on in this data set, but the nature of the significance is pretty fishy if I'm not honest about what I'm planning to do and what I care about and what's important before I start doing the analysis. Derek from Veritasium has this wonderful video. Derek is at least somewhat a Vancouver boy. He spent at least some of his life in Vancouver. So like all headlines, right? The answer here is no, but there's reasons you can look at published research and it can be wrong. If you're into a pretty deep dive on that, a pretty long watch, yeah, go for it. Here's my shorter dive on this. I have this phack.py that's linked from the slides, and in it, I'm basically running an experiment in this function. Except I'm running an experiment where I guess I'm definitely meeting the requirements of the t-test, right? I have data sampled from a normal distribution, and in fact, two normal distributions with equal variance, and then I do a t-test and I look at the p-value. And sometimes that p-value will be less than 0.05. And what I kind of expect here is that about 20% of the time, about 5% of the time, 1 out of every 20 times, I will get significance just by random chance. I happen to get it 2 out of 20 times here. That'll just happen. And the point being, if I do a lot of tests, even where I absolutely 100% know what's happening, I will see significance. Not always. Randomness is random after all. And then if I run this enough times, well, presumably about 1 out of every 20 times, I will do this. And the Bonferroni correction is effectively this. So instead of looking for p less than alpha, I say, well, I did 20 separate statistical analyses, so I will look for p less than 0.05 divided by 20. But still, if I do this entire process a bunch of times once in a while, I will get significance even at that bar, because probability is like that. Just by chance. And maybe this is just a lesson about being a good consumer of data or research or whatever. Just a single hey, we have a small p-value. It's not meaningless, but it means a specific thing, I guess. Sometimes you're going to get that just because that's how probability works. So one, I guess, just be careful with yourself, with your own, when it comes time for the project, just be on guard that you're being honest about how you're doing things. And I guess also, maybe this is a very clear description of what the Bonferroni correction is, right? So, don't look for this, look for this. Okay. One of the things that we talked about here like for the t-test specifically, but also for ANOVA, and we'll see it some other spots too, there's this assumption of normality here, that both of these things are drawn from a normal distribution. Both of these things are drawn from normal distributions, and they have the same variance. And I guess I can add in here this and turn off that assumption of equal variance, but I still have the assumption of normality. Again, that presumably has some effect on what's going on here. I don't believe I don't believe this to be true. Well, again, it's a little harder to come to a conclusion with that assumption, so I'm getting the significance a little less often, I guess. Let's not go crazy. Let's not try to turn one example into another. It turns out normal distributions are kind of everywhere, and what I mean by normal distributions are everywhere is the central limit theorem's out there being a theorem. And what it says is, if I have any probability distribution, doesn't matter how weird and pathological or whatever, if I sample some fixed number, n might be 5 or something, right? If I get 5 values, and then I take another 5 values and another 5 values and another 5 values, I take the mean of each group, those tend towards a normal distribution, which I think is shockingly weird. And I think I think probably this demo is, so I have this distribution of my values, and the game that we're going to play here is, again, I'm going to sample 1, 2, 3, 4, 5 things from this distribution. I'm going to take the average of those 5 things, and that kind of comes down to this third pane in this visualization. I'm going to do it again. Sample 5 things. What the central limit theorem says is that what I'm getting down in this third panel tends towards a normal distribution over time. So if I do, instead of 1 at a time, I'm just going to do 10,000. Oh, look, normal distribution. And I think it's really surprising that if I play that weird game with this absolutely completely weird, different than a normal distribution thing, it's really a surprise that a normal distribution should fall out of this process, but it does. Okay, so that means, like, just because we have a lot of statistical tests that assume normality, well, it means like a normal distribution is always hiding there somehow. If I really look hard enough, if I really need one enough, I can do this process. I can randomly sample from my group, average, and do it, and do that a bunch of times, and off we go. I should get a normal distribution that way. Cool. It's a nice 3 blue 1 brown description of what this is, and in the 3 blue 1 brown way, with a lot more detail than I am going to need you to care about. But if you care about those details, there you go. The effective conclusion of this is that if you have kind of a largish data set, you can just kind of pretend it's normal, and that's a little fishy. And I mentioned this last week, but the effective bar to do like a t-test or an ANOVA or something is not passes their normality test, like that stats.normal test function. The effective requirement to do a t-test or an ANOVA is you have enough data points, we'll call enough 40, 30, 40, 50, depending on the textbook you look at, seems to be the number. And your data is like reasonably close to being normal in this game. How do you clear everything? The closer this distribution on the top is, the more quickly it's going to converge to a normal distribution. So if we say, okay, well, the data looks pretty normal. It's if I look at a histogram, it's reasonably symmetric. The shape is vaguely like a normal distribution, and I have at least 40 data points. I'm going to call it normal. Even if the stat.normal test gives me a small p-value, I'm going to go for it. And I know that's not as quantitative as many of you would like to be. I really wish Like no statistician has ever given me a theorem or like a quantitative explanation for why I get to do this way, but I do, they assure me. Data is pretty normal, reasonably large data set, assume it's normal, and carry on. That's the actual thing you should do when analyzing data. So something like this data set from, well, I had it in lecture last week. Is that a normal, like, I think this failed, well, yeah, it did. It failed the normality test. Am I happy with this being normal? The thing is just n equals 40. If it was n equals 400, I might be a little happier. If it was a little more symmetric, I might be a little happier. But this is kind of like on the edge of what I would say, yeah, I will do a t-test and I will not be sad. I will not be nervous about it. Something like this. If I look at this histogram, it's very clear this is not a normal distribution, right? Nobody would look at this and say, yeah, it's pretty close to being normal. No, it's completely asymmetric. It's totally skewed off to the right. Even though the n, even though the n matches the requirement on this slide, it doesn't match the kind of close to normal requirement. So I would probably do a t-test here. I would definitely not do a t-test there. And I probably wouldn't run the normality test before I do it. Again, this data set, again, what we did last week when talking about transforming data was we logged both groups. And now, yeah, reasonably symmetric, reasonably equal variance, go for it. Do a t-test on this and don't look back. And I guess maybe I should, I didn't say it explicitly. The same rule for the equal variance test. You don't need the stats.Levine variance test to pass. You don't need the variance to always be within 1% or whatever. You need the variance to be reasonably close. And off you go. If you know, like, this is the other thing, right? Like you might know that, my data today has this distribution that isn't quite normal, but I know this population in general is normally distributed, and there's maybe something funny about my experiment or whatever, but in general, I would expect a normal distribution here. That might even be better than this. But again, if there's something like this, where it's pretty symmetric, I would just go for it. You can apply the central limit theorem as a magic wand if you want. There's a little bit of a judgment call to make there. But this isn't always the case, right? Like it's all well and good to say, oh, your data might be kind of close to normal, but your data might also be stupidly far away from being normal, and there might not be some nice clean transformation that will make it normal. I mean, in lecture slide examples, there often is, but those are examples in lecture slides. Maybe everything is crazy, and there's a data set in some exercise here where the numbers are discrete. They're like 0, 1, 2, 3. There's no 1.1 or whatever. And just the way that data is, there's just nothing you can do to make it normal. Well, non-parametric tests are there for us in that case. This is basically, there's no assumption about the distribution the data was drawn from. The Mann-Whitney U-test is one of those. The only thing is that basically you have a non-insane experiment. Like the experiment is reasonably decent. You have sampled in a decent way from a group, whatever that group is. And I don't even need numbers. I just need ordinal. So the difference here, I mean, I said it a couple weeks ago, but this is like SFU letter grades are ordinal but not numeric, right? I can't take SFU letter grades and throw them into a t-test because, well, you can't multiply them or add them or whatever, but you can sort them. So they would work here. And of course, what we would usually do is just convert to a GPA and then pretend they're numeric, but letter grades are ordinal, aka there's a big one, there's a small one, no need for how big or how small. That's the only assumptions. And if I have that, well, I have to change my null, right? So the null, like this is effectively a cousin of the t-test. Both the t-test and the u-test are two groups, and I want to know, is one group bigger than the other, or are they kind of the same size as my null? So for the t-test, the null hypothesis that expressed kind of the same size was equal means. Well, if all I have is ordinal, it doesn't make sense to talk about a mean. I can't do that calculation. So the null hypothesis here is if I have my two groups, x and y, if I choose a random x and a random y, and I look at which one is bigger, I expect that to be an equal probability kind of thing. It's equally likely that x is the bigger one, equally likely that y is the bigger one, exactly 1/2 probability. Or the way I kind of think about that, like it's not to say they're always the same size. Of course, some are bigger, some are smaller. If I took all the x's and all of the y's and I kind of put them in one list and I sorted them, I see them kind of equally spread out across that sorted list. That's what is in my head when I look at this probability equals 1/2. And the alternate hypothesis is, of course, the other thing, that the negation of that, which is the probability is not 1/2. Or again, the thing that sits in my head is if I took all of these things, put them together, sorted them, I would see kind of the x's tend to be a little bit more at the start of the list. The y's tend to be a little bit more at the end of the list. And of course, I know I can sort it because they're ordinal. But that's the null and alternate I get. If you don't like this null hypothesis, well, okay, but it's the one you get for a u-test, and it's really nice to have a non-parametric test hanging around. So for this data, again, from back a couple slides, well, okay, it's not normally distributed, and maybe I don't think about transforming it, or I don't feel like transforming it, or whatever. It is ordinal. These are fundamentally numbers. Numbers are ordinal. So import the thing, put them in there, and get a small p-value. Great. We also got, again, like the thing we did last week, which is log transform both groups and then then look at them to decide they're reasonably close to normal distributions, and then do a t-test. We also got a small p-value there. Okay, cool. Like it's nice to know we get a yes in either direction. We get yes. These two groups are kind of different sizes. The t-test said the means are different. The Mann-Whitney test said this thing. One group tends to be higher than the other one when you sort them, sort of statements. Okay, cool. This kind of sizes are different. The way you evaluate, the way you express size, those things are different. So that means that like you're definitely sort of have less power here, right? So like in this example where I just have 4 and 4, these 4 are kind of close in size, but I do have like all of these are smaller than all of those with n equals 4 on either group. These ones are much smaller than these with n equals 4, but I get exactly the same p-value. So you can see that sort of you're definitely leaving some power behind here, because the t-test, if these values were 100 times bigger than those values, you would see a tiny p-value because it's looking at that. Here, we don't care about how much bigger, how much smaller, just bigger or smaller. Okay, 1, I'm leaving that little bit of statistical power behind, but 2, this is one thing I can remember. If I have 4 things in one group and 4 things in the other group, and all of these are smaller than all of those, every time I ever see that pattern, I'm going to have p equals 0.03 from a Mann-Whitney test. That's nice. I have a thing, like I have a statistical test that I can do in my head, which is great. If I run some code, I run this thing 4 times and that thing 4 times, and this thing is faster all 4 times, then I know I have statistical significance there without doing a stats test, because I have this one p-value that I remember, which is nice. This is one thing that I guess it bugs me and it doesn't. Right? You see this all the time where people will they'll have the README in their GitHub repository, or their blog post, or their Medium, or whatever, wherever we post our written works now. And it will be like, hey, I have implemented the library that's a competitor to the other library. My code's better than the other library because look, it goes faster. Well, something you will see in exercise 6 or whatever it is, like fundamentally running code and looking at how long it takes it's effectively a stochastic process. It doesn't feel like there should be randomness in how our computer runs the same piece of code over and over again, but it takes a different amount of time every time. Are those times normally distributed? I don't know. But I need to be at least a little careful to just look and say, this thing can go faster than that thing. But if I do 4 samples from the same distribution, and these are all bigger than those, then I can come to a conclusion. Even if you're only taking this course because you need upper division computing credit and you're never going to analyze data again, well, you might at some point be benchmarking code. And remember, this is relevant. Okay, backing out a little bit more of like even less that I might know about data, I might have strictly categorical data. So that last thing was I have data that is big or smaller. This is not even, this is just, I have a bunch of survey results. I have just things, and everybody is in 2 different categories, I guess, is the sort of point here. And this is, I have like axis 1, what university do you go to? And axis 2, how happy are you? That's the sort of fake survey that I'm implying exists here. And I guess my question is, well, does student happiness and university like have anything to do with each other? And that's the fundamental game of the chi-squared test. And maybe as I hear myself say that, I know some of you are linguistically predisposed to look at those letters and pronounce them ch. That's not what they are. It's chi. And some of you will look at that and think that's an X. It's not. It's a Greek letter chi. Chi. Not ch, not X, please. So these are categorical totals. And I know it's easy to, and it's why I've explicitly said here, I have surveyed this many people. I have 292 data points here. I know I only see 6 numbers in the table. That's because I counted them up. There were 63 people who answered SFU in one column and happy in the other column, and 9 that answered SFU in that column and not happy in that column. Altogether that. And the assumption here is that, well, again, I have this situation where I have 2 categorical fields or columns or facts I know about a person, and that each one of those numbers, when I add them up, will be at least 5. So if I see a 2 here, I probably shouldn't do a chi-square test. The null is that there's that these 2 categories are independent, and I feel like people say independent, but they don't really know what it means. Here's what it means. I'm thinking of a person from this study. I want you to guess, like, how likely is it that they were happy? Okay, you have an idea? You have a sense in your head of how likely it was that they were happy? Okay, now I'm going to tell you they were from SFU. If that changes your belief about how happy they were, the null is not true. Right? So the independent category means if I tell you if I tell you where they are in column 1, you don't really learn anything about where they are for column 2. So the alternate hypothesis is there is some relation between them. So that thing that I had a few slides ago, same numbers as a few slides ago, is called the contingency table. It's, again, the counts. It's I took all of these things, I counted how many are in each of these categories, or how many are in each like pair of categories. I made a table of SFU, happy, not happy, no answer, UBC, happy, not happy, no answer. That is the input that I have to give to the chi-squared test, and I get a p-value. The p-value is less than 0.05, so I reject the null hypothesis, and I say, okay, now there is some relationship between those 2 questions. There's something about, if you tell me which line I'm on, that changes my sort of assumption about which column I'm in, or vice versa. So the expected frequency here is like, if I had these 292 people and everything was absolutely completely independent, I would expect to see a 7 in this position. What I had was a 9 in that position. So, you know, it's a little bit of a hint about where things got not independent, but fundamentally, it's the p-value. So I now come to a conclusion, and of course, the way I express this thought of there is some relationship between these categories, it kind of gives away something about what thing causes the other, and the stats test does not address that. I could say, okay, I got a small p-value, so therefore universities make you more or less happy. Or maybe it's being more or less happy changes which university you choose to go to. Or maybe living like far away from the city center makes you more or less happy, and that causes both, like, sorry, I guess being far away from the city center causes you to have a different length of commute, and that affects your happiness, and it also affects what university you chose. The p-value does not reveal which one of those is true, right? It doesn't say which causes what. It just says that there's some relationship between these categories. And this is just like how to read like a news story, right? Like, you see this all the time where it's like somebody at the university, you know, somebody in some like sociology department or whatever has done a study, and they have got a small p-value, and they publish their paper. Great, right? And then it goes to like the university's media office or whatever, and the university's media office says, I can't write this thing about a p-value, nobody will understand what it is. What does that mean? Oh, it means there's a relationship here. There's a relationship between this thing and that thing. And then, you know, we go one more unit away, and it's like, oh, so we're going to guess the causality, and we're going to write a headline that says this causes that. You should be very suspicious of any statement like that, because it's just not what the thing says. Maybe there's something else. Maybe there's some more study that could be done, or some other analysis you could do, or you could randomly take some people from this university and move them to that university and see how happy they are in 2 years or whatever. But it's not what a simple chi-square test tells you. Anyway, if we want to do this, again, we have 2 categorical columns, and we want to figure out what's going on. We've got to count everything up. I had an example. There we go. Okay, what I've done here. What? Okay, this I must have closed this without saving. Let me recreate my example. Just a sec. Okay. Sorry about that. Gee, you know, you do your best to prepare and be a good instructor, and here we are. Okay. What I have here in my example, I've just said, again, I've got what I want here is 2 columns of categorical things. So I've just said, like, I have 3 kinds of people in the world, whatever these are. I have, you know, A's and B's and C's, and then they're going to choose, again, they're going to choose what university to go to, or they're going to choose what kind of chocolate bar to buy, or, you know, whatever it is. And I have them making their choice this way. And as it is right now, everybody's making the same choice. Everybody's twice as likely to choose X as they are to choose Y and Z. And then I just generate random data that way. So I expect there to be no relationship here, because there isn't one. Now I can do a chi-square test. Okay. Got my data already. Oh, but wait, that's not what I need, is it? I need to count those up. So I have to, sorry, skip a couple slides ahead here. It turns out there's a crosstab function in pandas that is exactly what I need. If I have these 2 categories, I can count them up this way. It's just How many are in each of these things? And I have group and choice. Also, like, it doesn't matter what order I do these in, right? There is no relationship. I have this. Well, okay, from the way I set up my fake data, I expect there to be twice as many things in column X as there are in the other two, but the 3 rows should look the same. They look a little different, but again, I ask myself, how different are they? Is there a significant difference here between these two things? Let's find out. No, unsurprisingly. But, you know, I'm kind of imagining here that, okay, there might be something like this going on. For whatever reason, type A people are more likely to choose this chocolate bar or whatever. Then I expect to see a small p-value here, and I do. Because if everything was truly independent and it had these sort of ratios, I would expect this kind of thing. I would expect to see, yeah, like, you know, each row having kind of the same numbers. And that's now statistically not what I got. There is some relationship between these categories. Either the kind of person you are affects your chocolate bar choice, or the chocolate bar choice affects the kind of person you are. I don't know. You know, I guess I could, like, I could do this, right? I could make it a little more, let's do this, right? We're gonna go to Europe, and we're gonna go to 3 countries, and we're gonna ask, hey, what's your favorite chocolate bar? In that case, I think it's pretty, like, I could probably guess how this causality goes, right? I don't think people move to another country because they like a chocolate bar. I think they probably like a chocolate bar because they live in a country, but hey, who knows? And probability being what it is, I did not get a quite small enough p-value this time. It's just what I got, right? I have, again, in this sort of God's eye view of my experiment here, I know that these people are more likely to choose chocolate bar Y, and these people are more likely to choose X. It's just the accident of my data size or whatever. I only have 100. I only surveyed 100 people. Maybe if I surveyed 200 people, I could p-hack my way to a result. And this is not what I should do. But I guess for the purposes of a lecture demo, I think you'll forgive me. And I have this. Sure. This works equally well, I guess. You know, it happens that I have 3 nationalities and 3 chocolate bars here. You know, there's no rule. I could have this, like, and maybe I have this, right? Maybe these chocolate bars are not available in this country. Well, I guess I'm way more likely to come to some conclusion here. But what I do now expect to see, oh, do I not get a warning there? Sorry, I expected to get a warning because I don't have a 5 in that spot, and I really should. So I have violated the assumption of the test here. So maybe I should be a little more careful. I will do that. And again, I'll make my point. Like, it doesn't have to be just 2 and 2. It doesn't have to be 3 and 3. It can be however many categories you have this way, and however many categories you have that way, and you get a p-value that's either big or not. And again, I have like too subtle a difference here to detect, and the number of people I have surveyed. So even though, again, with perfect knowledge, I would know there's a relationship here or there's an effect here, I'm not seeing it today on this test. Sorry, and I'm just, you know, I'm making it like, if I make it like really likely that this country loves chocolate bar Y, they're way more likely to choose it. I suspect I'll see a small p-value. And I do. Okay, where was I at here? Well, almost done my hours where I'm at. Okay. Right. I have an example on the slide of the large p-value case, the thing I was just talking about, and it's the same as everything else. And I'm like, you know, I'm pandering to the computer science students here, by just saying like, oh, this is about programming. It's not, you know, it doesn't really matter what noun I choose on this slide, but you know, this isn't crazy, right? Like sometimes you do have a debugging thing that is just effectively feels like a random process, and maybe you just have to think of that as a thing that you have to do stats on because it's random, and then hopefully you can figure out what relationship you have in there, and maybe that will help you dial things in a little bit. This like if you have to do this, it sucks, but sometimes that's the reality. So I have, you know, this many failures and that many failures. I guess I will point out here that what I put in the contingency table isn't the number of failures and the total, it's the number of failures and the number of successes. So the total minus the failures. You know, these should add up to the total number of things that happened, I guess. And you know, this column should add up to the total number of failures that happened. There's 33 failures in the world here. Okay. So this doesn't mean there is no effect, right? Just like back in my Jupyter notebook, it doesn't mean there's nothing going on. It just means we didn't find it. You know, in a case like this where I'm doing some horrible debugging process, it doesn't tell me there's no effect of processor architecture on the failures that I'm seeing here, but it's probably enough to make me then look for some other hypothesis and go somewhere else, even though that's not the conclusion I have to draw from this. Maybe I just have to let the thing run for another week and thus p-hack my way into a result. This is unsatisfying, but it is what it is sometimes. Okay, like I said, and like I did there, sometimes you just have the contingency table handed to you. If you don't, you hope that you have a data set like this. We have two categorical columns, and like I have this individual is of type A and said yes, and this is type A and said yes, and this is type B and said no. Then the cross tab of those two columns is exactly what I want to do the analysis. Okay, that is an awesome spot to end the hour. Take a break. See you in the next video.